Hello everyone, my name is Nicholas Scarrett, and this is my Lab 2 Motion and Projectile. The purpose of this lab is to see Newton's second law of motion at work. We'll see how net forces affect an object's velocity over time. In our case, the object is going to be 2 wads of paper crumbled up in a ball. Now we're going to be studying this using Tracker and GlowScript. Now Tracker will be our visual model and GlowScript will include 2 computational models. Now the difference between these computational models with each other is very small, but one is actually going to include drag force, so the other's not. We'll see by the end of this lab that the one that includes drag in its computational model is actually more closely aligned with the observed visual model and tracker. This can be explained by Newton's second law of motion at work. The key fundamental principle of this lab is Newton's second law of motion. It states that the net force is equal to the change of momentum over the change of time, which is very important because when rearranged we can find our velocity update formula, which is going to be very important for the computations when we are calculating the net force such as gravity and drag, which will both change the velocity final and then finally applying this new velocity into our position update formula. Very briefly, the system and surroundings. Our system is going to be the crumbled up piece of paper, 2 of them combined to form a ball, and our surroundings is going to be everything, basically everything that affects this piece of paper while it's traveling in motion, and that some examples being gravity, air, and lift. And for the purposes of our computational model, we will only be taking account of gravity and air resist. So for the tracker video, we threw a piece of paper over a meter stick. Each and every single frame has a point, a center mass point of the paper ball, which each one of these points represents a point that is going to be placed on the graph, which represents a upside down parabola, which accurately captures the motion of the video with a y offset of 0.4. So these are the values we got from tracker. We have our initial position, our velocity initial, and our x component was solved by averaging out all of the x components velocities with each other and then averaging that out again. And then we found the y initial by solving for y final when it hits its peak, when it's equal to 0, and setting that y initial equal to gravity times delta t at that given t. And so in gravity in this case, we're going to be saying 9.8, and the proportional drag force constant, we through trial and error we found that it was 0.0010. All right, quickly going over our GlowScript code, we can see that we put in our initial position, initial velocity, our time steps, and our proportional constant. The one difference between these computational models is whether the proportional constant is set to 0.0010 or 0. Inside the while loop, we are calculating the gravity force vector and the speed direction to get us drag force. Now we add these 2 net forces together to then eventually update our velocity, and then our velocity is again going to be put into our position update. And this is what the graph is going to look like with drag. This is without drag. Here is a much clearer graph to compare the models. Now we can see that they're all leveled on top of each other. We can see at the beginning here, the tracker model was actually right on top of the no drag model. And then as time progresses, we can see that the with drag model actually starts to more closely resemble the tracker model. But it is important to note that they are still a bit far apart, so we may need to look into possible explanations after this. Now, to explain that, we can say that there's probably more forces acting on this object, the reason why they're not exact. And of course, there could have been human error in the forms of placing points or rounding error. And noted previously, it is important to note that I calculated x with all the averages rather than the first 2 initial. After reviewing the y component velocity, it never seems to plateau. So we can conclude that it would probably need a much higher y component to be thrown from to reach the critical mass where gravity cancels out with air resistance. So if we were to convert all of our exponents strictly into y component and get that magnitude, we'd see that the initial velocity for throwing it up would be much higher and the ball would actually go farther, meaning it would take longer for the net force of gravity to counteract that and allow for the ball to go back down into the surface.